So let's start with the class. Let others join. Um, so good afternoon once again. So all of you can see me, right? Am I audible and visible? Can you see my screen? Yes. Just let me know. Maybe others are joined in this class. Okay. Okay. Okay, I'll see to it. I'll put up a message. Just wait for a second. Hmm. Yeah. So, guys, if you can inform your friends, can you inform them to join in the correct link? That is our class link. If you can do it, just let them know. Okay, now let's start with the class. So let's go with. So today we are going to start a new topic, that is chemical bonding and molecular structure. Okay. So this is the first class for this lesson, and so let me start with the water. Okay. So the hydrogen bonding helps making water liquid, right? Hydrogen bonding makes the water liquid. So can you think how life would be if water was in gaseous state? Can you think of then can you think of existence of the life if it is in gaseous state? Obviously no, right? And one more thing, Van der Waals force of attraction between the different constituent of air makes the air possible. Existence of air. So, can you consider life without atmosphere? Obviously, no. So, this hydrogen bonding and Van der Waals force of attraction, these two are a type of bond. Okay. So, this is some of the example. We have some more chemical bonds also. So we are going to discuss those chemical bonds and its related information in this lesson. Okay. So moving on to the first thing. So under chemical bonds, the first few topics that we are going to see are octet rule, ionic bond, covalent bond, and coordinate bond. So I'll start with octet rule. So octet. So what is an octet rule? Atoms can combine with each other by transfer of valence electron from one atom to another. Okay, they can either gain or they can lose an electron. Okay, so here you see sodium and chlorine. Two atoms are there. Now sodium is giving one of its electron to chlorine and chlorine is gaining that electron. And now those two atoms are forming the bond. Okay, so why do atoms combine to form a bond? The reason is to attain the stability by releasing the energy. Okay, so the reason for the combination of two atoms to form the bond is to attain the stability by lowering the energy. Got it? And here these two atoms are forming the bond by the transfer of electron. Okay, they form the bond by transfer of electron. Or they can also combine, atoms can also combine by sharing of electrons. Okay, for example, let me take oxygen. So this is one oxygen atom. It combines with another oxygen atom and now they form oxygen molecule. So here the electrons are shared. Okay, so this is the shared pair of electron. Now here the bond is formed by the sharing of electrons. Okay, so why do they share or why do they transfer? By doing this transferring process or the sharing process, an atom is having 8 electrons around it. That is, it is gaining the octet configuration. So when a particular element is attaining the octet configuration, it is said that that particular configuration is stable for that system. Okay, so that's why atoms combine to form the molecule. Now you see around this oxygen. So around this oxygen, how many? So this is O double bond O molecule. Okay, oxygen molecule. And here 1, 2, 3, 4, 1, 2, 3, 4. So 6 valence electrons are there for oxygen. And this is these 6 are the electrons of 6 electrons of first oxygen. Let me represent the electrons of second oxygen with a cross. And these are the electrons of 6 electrons of the second oxygen. Now, after forming the bond, now you see there are 8 electrons around this oxygen as well as this oxygen. So, 2 oxygen atoms are having 8 electrons around them. Means they have attained the stable configuration, and this is called as octet rule. Okay. Now, some limitations are there for this rule. So, those limitations are, there are 3 limitations. So, the first limitation is the incomplete octet of the central atom. So here incomplete in the sense an atom may not have 8 electrons around it, but still it is stable. So those compounds are called as incomplete octet configuration containing compounds. Okay. So the example taken for this incomplete octet is lithium chloride, LiCl. Now you see here lithium, the valence electrons for lithium is 1. And that is represented by the green color dot you can see. And there are 7 valence electrons for chlorine. So 1, 2, 3, 4 and 5, 6. Here is the 7th. Okay, lone pairs are not shown here. Only the bond pair is given. So 2 electrons. Now these 2 atoms are combining to form the bond. Okay. Lithium doesn't have 8 electrons around it. Lithium has only 2 electrons around it, but still it is stable. So that's why it is coming under this incomplete octet configuration. Okay. I'll give you one more example. That is beryllium hydrate. The valence electron for beryllium is 2. And for one hydrogen, it is 1. Now, these 2 atoms, they are combining to form the bond. 2 hydrogens are forming the bond with 1 beryllium. Now, around this beryllium, if you see, there are only 4 electrons. Okay, it is not 8. It is only 4, but still the beryllium hydrate molecule exists in the atmosphere. Okay, so it is the limitation of octet rule again. One more example is BCl3. Boron, the valence electron of boron is 3. Okay, now you see around this boron, boron has only 6 electrons around it and not 8, but still it is stable. So lithium belongs to group 1, beryllium belongs to group 2, boron belongs to group 13. So group 1, 2 and 13 elements forming compounds are not fulfilling the octet configuration. Okay, but still they are stable. So the valence electron here it is 1 and here it is 2 and here it is In case of boron group, valence electron is 3. Okay, so now in some compounds, the number of electrons surrounding the central atom is less than 8. So this is especially the case with elements having less than 4 valence electron, that is group number 1, group number 2 and group number 13. Only these 3 groups have valence electrons less than 4. So these elements are forming the incomplete octet configuration with the stable compounds. Okay, so this is the first limitation. Now coming to the second limitation, any doubt? Any doubt from the octet rule and from the first limitation of octet rule? Ramnagar students, do you have any doubts so far? Shall I go on with the next thing? Okay. So the second limitation is odd electron molecule. So only 2 molecules will fall under this category. One is NO, nitric oxide, and the other one is nitrous oxide, which is NO2. Okay. So in both the compounds, if you see, nitrogen has odd number of electrons. So in the first molecule, you see how many electrons? 1, 2, 3, 4, 5, and 6, 7. So around this nitrogen, we have only 7 electrons, which is odd number. Okay, it is not 8. Around this nitrogen, you see 1, 2, 3, 4, 5, 6, 7. So again, this nitrogen, if we calculate the number of electrons which is there in bond pair and electrons which is present in lone pair, if you calculate, it is again 7, which is odd number. So it is not 8, it is 7. So they are odd electron species, but still they are stable. NO and NO2 is there in the they are stable compounds. Okay, so this is the second limitation. And coming to the third limitation, that is expanded octet. Expanded means more than 8. The central atom contains more than 8 electrons, but they are stable. The first example for this is PF5. You see here, the number of bonds around phosphorus is 5. Okay, so each bond contains 2 electrons. So 5 bonds means around this phosphorus, how many electrons we would have? 10 electrons, right? It is more than 8. Okay, that is expanded octet, but a stable compound. And S sub 6. So sulfur has 6 bonds around it. So 6 into 2 will become 12 electron. 12 electron containing species. And one more compound is H2SO4. So around the sulfur, you see again 6 bonds are there. So each bond contains 2 electron. So again 12 electrons. Okay. So these are some of the compounds which has more than 8 electron containing species. Okay. So for the first compound 10 electron, second compound 12 electron, and for the third compound also 12 electron. So these three are the limitations of octet rule: incomplete octet, odd electron species, and expanded octet. You have to learn the examples which are falling under each category, because they will ask in the choose the correct answer, and or in the match the following type also they can ask. Okay, so very easy, you can learn. Now we will see one previous year question of J mains from this topic. So which is there on your screen. Which of the following pair of molecules contain odd electron molecule and an expanded octet molecule? Can anyone give me the answer for this? Very easy, right? Which of the following pair contain odd electron and expanded octet molecule? The first compound should be an odd electron molecule and the second should be an expanded octet molecule. Find out the answer fast. Just now we have studied, no? Okay. The correct answer is option B. So NO is an odd electron molecule and H2SO4 is an expanded octet molecule. Okay. So next we will go with the types of bonds. So a chemical bond is first classified into two. Okay. Strong bond and the other one is weak bond. Strong bonds are again classified into four: ionic bond, covalent bond, coordinate bond, and metallic bond. Weak bond is classified into two: hydrogen bond and van der Waals interaction. And the other one is van der Waals interaction. Okay, so these two are the weak bond. Weak bond, strong bond in the sense, strong bond means the bond energy will be very, very high. What is bond energy? The energy required to break the bond is very, very high in case of strong bond, and in case of weak bond, we can break it so easily. Got it? So now let us discuss about the ionic bond. So what is an ionic bond and how does it form? So it is formed by the transfer of electrons from a metal to a non-metal in order to obtain a full valence shell for both atoms. Okay, the concept is okay. Okay, students, no issues. So all of you are watching from this ID, right? All 20 of you are there from this ID, right? Yes, okay. Then no issues. So I'll just repeat once again. Okay, don't worry. So, so I have asked this question to you, right? So have you found out the answer for this? Odd electron species? Or this is your teacher's phone? Okay. So from a single phone, 20 students are watching. He gave us to. Oh, okay. Okay, no issues, students. Fine. So NO, the correct answer is option B. Correct answer is option B. So will you be able to follow up the class today? I think you can do it. No? Okay, try to attend, and you can also get the class in the YouTube also. Connecting notes. Okay. Okay, try to attend. Try as much as you can. So I'll go with the next slide. Types of bond. So chemical bond is classified into two. Okay, strong bond and weak bond. So strong bond is again classified into four. The first is ionic bond, the second is covalent bond, next is coordinate bond and metallic bond. Okay, these four are the strong bonds. And coming to the weak bond, there are two categories. One is hydrogen bonding and the other one is van der Waals interaction. Okay, so strong bond, weak bond in the sense, strong bond means the energy required to break the bond will be very, very high. And in case of weak bond, we can break the bond so easily. Okay, that is the difference between these two. So we will discuss one by one. Okay, first we will start with ionic bond. So what is an ionic bond and how does an ionic bond form? So an ionic bond is formed by the transfer of electrons from a metal to a non-metal in order to obtain a full valence electron for both the atom. A same example, sodium with fluorine. You see, sodium has 11 electrons. Okay, the atomic number for sodium is 11. And the atomic number of fluorine is 9, so it will have 9 electron. When one of the sodium loses its electron to fluorine, now both the atoms are getting 8 electrons in their valence shell. Right? You see there, sodium also has 8 electrons. We attended first class because even if we click the link, it response for the things getting continuity. Okay. Okay. Okay, I'll inform this. I'll inform this issue to my manager once I finish this class. Okay. So don't worry about the others now. You attend the class and I will take this issue to the manager later. Okay. Shall I continue? You are not able to listen to my lecture? Okay. Okay. Okay, fine. So if you find any switching of classes when I was teaching, just let me know. Okay. Let me know. So the next topic is lattice enthalpy. Okay, what is lattice enthalpy? The energy required to completely separate one mole of the solid ionic compound into gaseous constituent atoms. Okay, suppose if I am taking sodium chloride. Okay, so the solid ionic compound that I am going to take is sodium chloride. So 1 mole of sodium chloride I am taking. Now the energy that I am giving to separate the solid 1 mole of solid sodium chloride into its gaseous atom ions, that is Na plus ion and Cl minus ion in the gaseous form. So energy required to separate this 1 mole into its gaseous constituent species is called as lattice energy. Okay, you can see it in the GIF. Okay, that is a lattice. Now I'm giving energy. The lattice is absorbing the energy that I'm giving and it is breaking down into its constituent atoms. Okay, so which is called as lattice energy. Now, the key factors for the formation of ionic bond. If ionic bond has to form, it has to have some 3 criteria. The ionization energy should be very, very less for the atom. Suppose if I'm taking the sodium chloride, here sodium is the metal, right? So sodium's ionization energy value should be very, very less. Energy required to remove an electron from the sodium should be very less. And electron gain enthalpy should be very, very high for this chlorine. Chlorine is a non-metal and the electron affinity value or electron gain enthalpy value should be very, very high for chlorine, for an ionic bond to form. Okay, and the lattice enthalpy should be very, very high. Lattice energy, that is energy required to break the system. Okay, 1 mole of the system should be very, very high. So these 3 are the criterias for the formation of ionic bond. Okay, so always an ionic bond is formed between a metal and a non-metal. That is the elements which are present at the left side of the periodic table and with the elements that are present at the right side of the periodic table. So those 2 combination will give rise to the ionic bond. Got it? Now let's move on to covalent bond. Covalent bond. So covalent bonds are formed by the sharing of electron pairs between the atom. Ionic bond is formed by transfer of electron. Here it is formed by sharing of electron. Suppose if I am taking chlorine atom, so this is a configuration, neon 3s2 3p5 is the configuration of chlorine atom. And if this chlorine gains 1 electron, it will have 3p6, which is completely filled configuration, and it would be the configuration of argon, which is stable. Okay, so what this chlorine atom will do, one chlorine will try to interact with another chlorine. So 2 chlorine will come in contact with each other now and they will share their electron. So these 2 electrons of both the chlorine, they will get shared, and here you see this is the shared pair of electron and they have formed the bond. Shared pair of electron leads to the formation of a covalent bond, and they are forming the stable chlorine molecule also. Okay, now if 2 atoms share only 1 pair of electron, then only 1 bond, that is single bond, will be formed. Okay, if 2 atoms shares 2 pairs of electron, then it gives rise to the double bond that I will show you in the next slide. Here you see, now the 2 carbon atoms are sharing the 2 electron pairs. Here you see 2 electron pairs. So they give rise to the double bond. Okay, and if 3 electron pairs are shared, triple bond will be formed. Here you see 3 electron pairs. They are shared between the 2 atoms and giving rise to the triple bond between the two carbon. Okay. So these are the covalent bonds. Now coming to the next type of bond, that is coordinate bond. So no doubt from ionic and covalent bond, right? Ionic bonds are formed by transfer of electrons and covalent bond is formed by the sharing of electrons. So if you're having any doubt, you can let me know in the chat box. I'll move on to the next bond. Shall I? Any doubt? Yes or no? Okay. Coordinate bond. Now what is this? I'll take one example. Ammonia boron trifluoride. Okay, ammonia boron trifluoride. So the first molecule is ammonia, NH3. And we all know the valence electron for nitrogen is 5, and among that 5, 3 has gone for bonding, and 2 electrons are present as one lone pair here. Okay, nitrogen's lone pair. And boron trifluoride is BF3. Okay, BF3. Number of valence electron for boron is 3, and all the 3 valence electrons has gone for bonding with fluorine. Now, what happens? The nitrogen, which has the 2 lone pair of electron, it will come and form the bond with the empty orbital of boron. Okay, it will come and form the bond with the empty orbital of boron. Now the 2 electrons which is required to form one bond is coming from the same atom. Okay, it is coming from the same atom, and this type of bond is called as coordinate bond, and we represent that bond by putting an arrow like this, because both the electrons are going from the same atom, right? It is going from nitrogen to boron. So we represent the coordinate bond like this. Got it? So, and this bond, this coordinate bond is also known as dative bond. The other name for coordinate bond is dative bond. Once again, okay, I'll repeat. If both the electrons are coming from the same atom, we call that bond as coordinate bond. So if 2 atoms has to form the bond, 2 electrons are required, right? And in case of covalent bond, 1 electron is coming from one atom and the other electron is coming from the other atom. But in case of coordinate bond, both the electrons will come from the same atom. That is here in this example, 2 electrons are coming from nitrogen. Okay, from the same atom, and we call that bond as coordinate bond, and it is denoted by this arrow. Okay, clear now? Nitrogen is transferring its 2 electrons to boron. Okay, fine, good. Now coming to the next topic, that is dipole moment and Fajans rule. Dipole moment and Fajans rule. So far what we have seen is that okay? We have seen octet rule, we have seen ionic bond, covalent bond, and coordinate bond. So that part is clear, right? Very easy, and it is so simple only. Yeah, good. Now let's go with dipole moment and Fajans rule. So in this topic, we have 4 subdivision. One is bond parameters, and then we will talk about resonance. Then we will go in detail with the dipole moment, and then we will jump to Fajans rule. Okay. So now starting with bond parameters. So who are the bond parameters? There are 4 parameters we have. Okay, to define a bond, we need 4 parameters. So the first is bond length. Okay. The second is bond angle. The third is bond enthalpy, and the fourth parameter is bond order. Okay. From the picture itself, you might have understood what I'm going to tell in each of the thing. Yeah. So, but still we will discuss in detail one by one. So we'll start with bond length. So what is bond length? It is the equilibrium distance between the nuclei of 2 bonded atoms in a molecule. So I'm going to take a molecule. There are 2 atoms. One is A and the other one is B. Both the atom will have nucleus. At the center of the atom, we will have the nucleus. And this is the equilibrium distance. This is the equilibrium distance between the 2 atom, between the 2 nucleus of both the atom. And if I draw a black color line, you can see, right? So that will be the radius of A atom, and this is the radius of B atom. Now this is R. Okay, what is this R? This R is equal to RA, small RA plus RB. So this capital R is called as bond length. That is the equilibrium distance between the nucleus of the two bonded atom in a molecule, which is called as bond length. Okay, clear? Clear, right? Okay, good. So some of the bond length values are here for hydrogen, fluorine, chlorine, bromine, iodine, nitrogen and oxygen, you see, for all the heteroatomic system also given. So it is there in your book also. You don't have to memorize these values, okay? Just observe the values and think of it. I will tell you one relation which relates bond length, bond enthalpy, bond order at the last, okay? You don't have to memorize. Just observe whether it is increasing or decreasing. That part alone you keep in mind. Observe it later. I will tell you at the end. Now coming to the bond angle. So it is the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or a complex ion. Okay. Suppose if I take water molecule. Okay. So the formula for water molecule is H2O. Now this HOH, it is making an angle of 104.5 degree. Okay. So that is the angle between the orbitals containing the bonding electron pairs around the central atom. So this is oxygen. These two are the bond pairs. So oxygen has 6 valence electrons. Among that 6, 2 has gone for bonding. Remaining 4 will be present as 2 lone pair, right? So these two are the lone pairs and these two are the bond pairs. These two are the bond pairs. Now the angle that is created by this bond pair is called as bond angle. Okay, it is called as bond angle. And for water molecule, it is 104.5 degree. If we take methane molecule, CH4, what is the bond angle of HCH bond angle? It is 109.5 degree. If we take ammonia molecule, in which the formula is NH3 with one lone pair, here H and H bond angle is 107 degree. Okay. So these three molecules bond angles are very, very important. Just to have a note of it. Water 104, methane 109.5, and for NH3 it is 107. Very important. Okay. So due to the lone pair repulsions, the corresponding compound is having such bond angles. So those repulsion concept and all I will explain you in this lesson. I will explain you in BSCPR theory. Under that topic, I will explain that thing. Don't worry about it. Now let us move on to the third parameter, that is bond enthalpy. What is bond enthalpy? It is also called as bond energy. Energy required to break 1 mole of bonds between two atoms in a gaseous state is called as bond enthalpy. So I have taken an example, hydrogen molecule I have taken. Now there is one bond between two hydrogen atoms, right? If I want to break this bond, I have to supply some energy, and that energy is called as bond energy. Energy required to break the bond. Okay, energy required to break the bond. Now here the energy required to break this hydrogen bond is 435.8 kilojoule per mole of energy is required. Okay. If a molecule contains more than one bond, for molecules containing multiple bonds like oxygen has 2 bonds, right? So here you see the energy is little bit high. Here it is 435, but here it is little bit high because we have to break 2 bonds, right? So it is little bit higher than that. And if I go for triple bonded system like nitrogen, there are 3 bonds. You see, the highest amount of energy is required to break this nitrogen triple bond. It is 946 kilojoule per mole. Very high. Okay. Very difficult to break the NN bond. So this is the bond enthalpy. And some more example also I'll give you. For polyatomic molecule. So far we have seen diatomic. H2, O2, N2. All these are diatomic species. Okay. If we go for polyatomic, that is more than 2 atom containing species are called as polyatomic species. So in that case, The measurement of bond strength is okay. Okay, fine. So the measurement of bond strength is very complicated. Okay. So in case of H2O molecule itself, you see. So how many OH bond we are having? How many OH bond we are having in H2O molecule? We have two OH bond, right? This is one bond and this is the second bond. So what I have to do, I have to break the bonds one by one. So if I break this bond first, if I break this bond first, this is first bond and this is second bond, I'll take. So if I break the first bond first, I will get one hydrogen atom and then one OH will come out. So this is that hydrogen and OH. Now the energy required to break this first bond is 502 kilojoule per mole. Then what I have to do? So there is one bond here, right, between oxygen and hydrogen. I have to break that bond also. So I am taking that molecule and breaking that bond also, and it leads to the formation of hydrogen atom and oxygen atom. Now here the energy required is little bit less. It is 427. Now in the question, if they ask you to find out the bond energy for H2O, which option you will select? 502 you will select or 427 you will select? Obviously, both the options are wrong. Okay. So, both the options are wrong. So, in this case, what we have to do, we have to find the mean bond energy value. Or we can tell it like average bond energy value. So, how to find out the average bond enthalpy? It is equal to the total bond dissociation enthalpy divided by the number of bonds broken. Total bond dissociation enthalpy by number of bonds broken. So total means you have to add both the delta H value, that is 502. For water molecule it is 502 plus 427, and two bonds we have broken, no? So divided by 2. So we are getting one value, and this is the bond energy value for water molecule. Very good. It's very good, students. 464.5. Got it? So this is how we have to calculate the bond energy for polyatomic species. Suppose if they are giving for NH3, if they have given NH3, what you will do? NH3 contains 3 NH bond, right? So we have to break 3 bond. So you just add all the delta H values which is given there in the question and divide by 3. You will get the answer. Okay. So fine. Next we will jump to bond order, which is the fourth parameter, fourth bond parameter. What is bond order? The number of bonds formed between the two atoms is called as bond order. Very easy. The number of bonds between two atoms in a molecule is called as bond order. Suppose you see here hydrogen molecule. Here hydrogen has one bond. So the bond order is 1. Oxygen 2. Nitrogen 3. In carbon monoxide also the bond order is 3 because the number of bonds between both the atoms is 3. Very easy. Okay. And coming to one more information about the bond order, isoelectronic molecules and ions have identical bond order. What is meant by isoelectronic? Iso means same. Electronic means electrons. Same number of electron containing molecules or ions will have same bond order. For example, you see here fluorine F2. How many electrons are there for fluorine? For one fluorine, the atomic number is 9. For F2, atomic number is 9 plus 9, 18, right? So it is total number of electron is 18. And O2 2 minus, you see, atomic number for one oxygen is 8. So the number of electron would be 8. And for two oxygen, it is 16. And now this oxygen has gained 2 electron, O2 2 minus. So 16 plus 2 is 18. So now these two are isoelectronic. They are having same number of electrons. So the bond order for both the species is 1. Got it? So now in case of nitrogen, you see, nitrogen atomic number is 7. Nitrogen molecule 7 plus 7, 14. And for one carbon, atomic number is 6. And for oxygen, atomic number is 8. So 6 plus 8 is 14. So both are isoelectronic. So both the bond orders are same. It is 3. Nitrogen triple bond nitrogen N and C triple bond O. Both will have the same bond order. Got it? Now I'll tell you the relation between bond enthalpy, bond order and the bond length. When order is more, bond enthalpy is also more, but bond length will be very, very less. So what is the relation? Bond order is directly proportional to bond enthalpy, but these two are inversely proportional to bond length. If bond order is more, energy required to break the bond is more, and the bond length will be very, very short. Got it? So very important relation you have to keep in mind. Just write it and put an important symbol over there and keep. Okay. So is this clear for all? All the 4 bond parameters is clear for JNV Ramnagar students? Yes, good. Now we will go with resonance, the second topic, resonance. So what is resonance? What is resonance? So while we were discussing GOC lesson, I have told you, no, the delocalization of pi electron is called as resonance. The delocalization of the pi electron is called as resonance. So when a single Lewis structure cannot explain the molecule accurately, we use a canonical and hybrid structure of molecule. And this canonical structures are otherwise called as resonance structures. Now I'll take ozone molecule. The ozone molecule is O3, right? O3 is the formula for ozone. And this O3 molecule, one of the structure of this O3 is this. And one more structure I can write, and this is the second representation. Now these two are called as resonance structure, or we can tell it like canonical structure. These two are called as canonical structure or resonance structure. Resonance structures will not exist in the reality. Okay, canonical structures or resonance structure will not exist in the reality. Only the hybrid structure will exist in the reality. Now, how to represent the hybrid structure of this ozone? You just take that pi bond out and put a dot. Okay, put a dot. So just represent only the sigma bond and represent the pi electrons by using the dots or some dashed lines. Okay, which will give you the resonance hybrid. So only the resonance hybrid exists in the reality. Got it? In the resonance hybrid, you can see that both the over bond lengths are same, 128. Whereas in this resonance structure, one is different from the other. Okay? So when I shift this pi electrons here, I will get this structure. When I shift this electron here, I will get the first structure back again. So this is the delocalization of pi electron, which leads to the resonance structures. Okay. Now the next topic is dipole moment. The next topic is dipole moment. So any doubt from the resonance part for Ramnagar students? No doubt? Okay. So I'll jump to the dipole moment. So any bond you can take, whether it can be a covalent bond or ionic bond. If you are taking an ionic bond, there will be some covalent character present in it. And if you take any covalent bond, there will be some ionic character present in it. Okay. Now, there is some polarity in the bond. Okay. Polarity in the bond is there. So, it is divided into two. Polarity in the bond is divided into two, and it is studied with this classification. One is non-polar covalent bond and the other one is polar covalent bond. So I'll start from non-polar covalent bond. So what is meant by non-polar? If a compound doesn't have plus minus in it, it is called as non-polar. So it is formed by the homonuclear atom. Homonuclear means if you are taking same atom, if you are taking two atoms and if both the atoms are same, then they will form non-polar covalent bond. Hydrogen and hydrogen leads to hydrogen molecule. So that is non-polar. Okay, A, B, B. So both the bonded atoms are same. Now you see A atom is having one electron. The second A atom is also having one electron. So both will form a bond. And B also in the same way they will form one bond. Now they have formed the bond. Now you see when they form the bond, we call that as non-polar covalent molecule. So who are the non-polar covalent molecules? Hydrogen, fluorine, Chlorine, oxygen, nitrogen, all these are the examples of non-polar covalent because both the bonded atoms are same. Now coming to the polar covalent molecule, atom A will be different from atom B. So both the bonded atoms now they are different. In most of the cases, the atom A, which is very small in size, that would be less electronegative and atom B would be more electronegative. So the one which is more electronegative, it will try to attract the shared pair of electron towards itself, right? That is called as electronegativity. And now this atom B is more electronegative, so it will go and take the electron of atom A also. Now you see here, the red color atom, electron of atom A has come toward B. You see here, before it is with A, now B is electronegative, no? So it has gained atom A electron also. So the one which is gaining the electron will get the negative charge, and the one which is donating the electron will get the positive charge. So the small delta denotes partially, so partially negative and partially positive. Now the bond is polarized. So we are having positive end and negative end. So plus minus, dipoles are being formed. So it is called as polar covalent molecule. Polar covalent molecule. The examples of polar covalent molecules are HCl, H2S, H2O, and NF3. Okay. So in all these in all these molecules, one atom is different from the other. Okay. Bonded atoms are different. One is more electronegative than the other. The one which is more electronegative is gaining the electron and getting the negative charge. Okay. Now, the measure of this bond polarity, using a number is called as dipole moment. Measure of the bond polarity is denoted by the letter mu, and it is called as dipole moment. Okay. Now, for symmetrical molecules, symmetrical means if I cut the molecule into two, I will get two equal half. So BF2, beryllium difluoride, here it is symmetrical because if I cut, I will get two equal half. In this case, dipole moment will be 0. Here also you see BF3, if I cut this molecule in this manner, I will get two equal half, right? So the dipole moment will be 0. So the total dipole moment, they are equal and opposite in direction. So the net dipole moment will be 0. Got it? So some more informations are there for dipole moment that I will discuss you in the next class because it is already time. You have to go for the next class, right? It's 3:56. So I'll stop here. You go and study till the topic which we have discussed. So what we have discussed today? Today we have discussed all the types of bonds and its types, right? So first what we have discussed, octet rule, bonds and its types. Then what we have discussed, all the resonance we have discussed, and now we are discussing the dipole moment. Okay, dipole moment. So all these things you study and come for the next class. We will continue the dipole moment in the next class. Bond parameters, I forgot. Yeah, fifth one is bond parameters. Bond angle, bond enthalpy, bond length, and bond order. So all these things you study, revise and come. Okay? Okay then. Any doubt, student? You have any doubt? No. Okay then. Thank you so much for listening the lecture. See you in the next class. Take care. Bye-bye.